Hello and welcome. In today's video, we'll categorize and explore the common laboratory chemicals used in research, along with their specific purposes. This video is prepared by chemical engineer Weynshet Ferede. Let's get started by exploring the common laboratory chemicals used in research. 1. Acids. First, let's talk about acids. Acids are substances that release protons or hydrogen ion when dissolved in water. They have a pH of less than 7 and are essential in various reactions. For example, hydrochloric acid, commonly used in acid-base titrations, helps adjust pH levels and is involved in preparing various compounds in the lab. On the other hand, sulfuric acid is a strong acid used in dehydration reactions, oxidation reactions, and also serves as an electrolyte in lead-acid batteries. Meanwhile, formic acid plays a role in organic synthesis, acting as a preservative and a catalyst for certain reactions. Other examples include orthophosphoric acid, which is key for preparing phosphate compounds and preventing corrosion, and citric acid monohydrate, commonly used as a buffer in both biochemical and industrial processes. Finally, boric acid, a weaker acid, is used in buffer solutions and also serves as an antiseptic in laboratory settings. 2. Bases. Next up, we have bases. Bases are substances that accept protons or donate electron pairs and typically have a pH greater than 7. They are crucial for neutralizing acids and forming salts. Sodium hydroxide, a powerful base, is widely used in soap-making, acid-base titrations, and other chemical reactions that require an alkaline medium. Potassium hydroxide, found in pellet form, is similarly strong and is important in preparing potassium salts and in laboratory cleaning processes. Sodium carbonate, or soda ash, is another useful base, especially in neutralizing acids and acting as a reagent in analytical chemistry. And we can't forget sodium hydrogen carbonate, better known as baking soda, which is a milder base often used in neutralization reactions and even in antacid preparations. Sodium carbonate anhydrous, a form of soda ash without water, is commonly used in laboratories as a reagent in various chemical reactions, especially for neutralizing acids and for adjusting pH in different processes. It's also crucial in the production of glass and soaps, and in water treatment applications. Sodium acetate trihydrate is another important base, typically used as a buffer in biochemical and industrial applications. It helps maintain a stable pH in various reactions and is widely used in laboratories to stabilize the pH of solutions, particularly in biochemical assays. Finally, potassium hydroxide in liquid form is a strong base, commonly used in chemical laboratories for tasks that require an alkaline medium. It's often employed in the preparation of potassium salts, as well as in saponification reactions, where it helps produce soaps from fats and oils. Additionally, it's used in various cleaning and etching processes due to its strong caustic nature. These bases are essential tools in many chemical reactions, offering diverse applications in both industrial and laboratory settings. Through salts. Now let's look at salts, which are formed by the reaction of acids and bases. These compounds are essential in a wide range of applications in the lab. Ammonium acetate, for instance, is often used as a buffer solution in chemical reactions, particularly in the synthesis of salts and esters. Ammonium chloride, on the other hand, is frequently used in preparing ammonia-based solutions and as part of buffer solutions. Another commonly used salt is sodium sulfate, a drying agent in laboratories. It's essential for removing moisture from organic solvents. In the laboratory, sodium hexametaphosphate is primarily used as a dispersing agent and a water softener. It is often added to solutions to prevent particles from clumping together and to stabilize suspensions, making it useful in various chemical and biological applications. In the laboratory, sodium thiosulfate pentahydrate is frequently utilized as a reducing agent in titrations, especially in the determination of chlorine and iodine concentrations. Similarly, Sodium nitrate AR is commonly used in various chemical reactions and is an important reagent in preparing other sodium compounds. Sodium acetate trihydrate serves as a buffering agent, helping to maintain the pH in a variety of chemical processes and biological experiments. Ferrous chloride AR or tetrahydrate, on the other hand, is a source of iron, 2 ions, and is essential in redox reactions and in the synthesis of organic compounds. Magnesium sulfate heptahydrate is often employed in laboratory work as a source of magnesium ions for chemical reactions. Moving on to calcium carbonate, it is a commonly used reagent for acid-base titrations and as a source of carbonate ions in laboratory experiments. Potassium iodide AR plays a crucial role in the preparation of iodine solutions and in various redox reactions. Sodium chloride is a fundamental reagent in preparing solutions and is widely used in experiments that require a stable ionic medium. Sodium silicate monohydrate finds its application in the synthesis of silica-based materials and in chemical analysis. Sodium sulfide is utilized for its reducing properties in organic synthesis and for the preparation of other sulfur-containing compounds. Lastly, zinc chloride is widely used as a catalyst in organic reactions and in the galvanizing of iron, protecting it from rust. 4. Organic solvents. Organic solvents are crucial in dissolving other substances, especially for extractions and organic synthesis. N-Hexane, for example, is a non-polar solvent commonly used to extract oils and fats from plant materials in organic chemistry. Toluene is another popular solvent used in organic synthesis and in paint thinners, especially in reactions that require non-polar solvents. Acetonitrile, or ACN, a highly polar solvent, is essential in high-performance liquid chromatography or HPLC and organic synthesis. Diethyl ether is also frequently used as a solvent due to its low boiling point and versatility in chemical reactions and extractions. Chloroform, often used in organic chemistry, serves to separate aqueous and organic layers, making it invaluable in DNA preparation. Denatured alcohol, which is ethanol mixed with chemicals to make it undrinkable, is widely used as a solvent and cleaner in various chemical reactions. 5. Reagents and indicators. Moving on to reagents and indicators, these chemicals help facilitate reactions or indicate the presence of specific ions or compounds. Benedict's reagent, for example, is a solution that reacts with reducing sugars like glucose, changing color to indicate their presence. Methyl red is a pH indicator that changes color based on the acidity or alkalinity of a solution, making it useful in both microbiology and chemistry. Another important reagent is ethylene diamine tetraacetic acid, or EDTA, a chelating agent that binds metal ions and is widely used in titrations and various biochemical applications. 6. Miscellaneous chemicals. Lastly, let's look at miscellaneous chemicals that serve various roles in research. Magnesium sulfate, for instance, is primarily used as a drying agent, absorbing water from organic solvents to ensure purity in chemical processes. Glycerol is a versatile solvent used for preserving biological materials and in laboratory experiments. Distilled water, being free from impurities, is the go-to solvent for many chemical processes, ensuring no contamination from minerals found in tap water. Activated charcoal is used to purify liquids and gases by adsorbing impurities, while triethanolamine plays a role as a pH buffer and emulsifier in different formulations. Castor oil, although less common, is used as a solvent in laboratory processes, especially in the preparation of biodiesel. In the laboratory, soluble starch is primarily used to test for the presence of amylase activity in bacteria. When amylase-producing bacteria break down starch into simpler sugars, this reaction can be observed through specific biochemical tests, helping to identify the microorganism. On the other hand, solutions with pH 4 and pH 7 are commonly employed for pH calibration. A pH 4 solution, being acidic, is used to calibrate pH meters to ensure accurate measurements in acidic environments. Similarly, a pH 7 solution, which is neutral, is used for calibrating pH meters to provide reliable readings in neutral conditions, ensuring proper growth conditions for bacteria and accuracy in experimental results. Peptone, on the other hand, is a crucial nutrient source in microbiological media. It provides essential amino acids, peptides, and other growth factors that support the growth of a wide variety of bacteria. Peptone is commonly used in the preparation of broths and agar plates to culture bacteria, making it indispensable in bacteriological research and experimentation. So, you might have seen labels like AR, CP, ACS, and RE on some of these chemicals. Let me break down what each of these labels means. AR, or analytical reagent, indicates that the chemical is of high purity, making it suitable for analytical work and precise experiments. These chemicals are free from impurities that could interfere with lab analyses. CP, or chemically pure, refers to chemicals that are of good quality for general laboratory use. While they are purer than commercial-grade chemicals, they are not as high in purity as AR chemicals. CP chemicals are typically used in non-critical experiments. ACS, or American Chemical Society, is a label for chemicals that meet the strict purity standards set by the American Chemical Society. ACS-grade chemicals are highly purified and are perfect for research and analysis, where precision is crucial. RE, or reagent, refers to chemicals that are typically used for specific reactions or tests in experiments. These chemicals may not be as pure as AR or ACS-grade chemicals, but they are still suitable for general laboratory use. In summary, these labels help you choose the right chemical grade depending on the level of precision and sensitivity needed for your experiments. Now, let us discuss which chemicals can replace others in laboratory settings. It's important to remember that when substituting one chemical for another, the concentration and purity should ideally be similar to ensure consistent results in experiments. 1. Acids. Hydrochloric acid can be replaced with sulfuric acid or nitric acid in many acid-base titrations and pH adjustment processes, but the concentration and strength should be carefully matched for accuracy. Sulfuric acid, used in dehydration reactions, could be substituted by phosphoric acid, though the latter is weaker, so the concentration may need to be higher to achieve similar effects. A formic acid can often be replaced with acetic acid in organic synthesis, though since acetic acid is less reactive, the concentration might need adjustment for the desired reactivity. Orthophosphoric acid can be substituted with citric acid in buffer solutions, but their buffering capacities may vary slightly, so make sure to adjust concentrations for consistency. A boric acid, a weaker acid, could be replaced with citric acid or acetic acid for certain buffer solutions, as long as the concentration matches to ensure a similar pH control. 2. Bases. A sodium hydroxide can be replaced with potassium hydroxide or calcium hydroxide in many reactions. However, as NaOH is more commonly used in titrations, ensure the concentrations are similar to maintain the desired strength. A potassium hydroxide can be substituted with sodium hydroxide for most applications, though the form, liquid versus pellets, and concentration should be considered. Sodium carbonate, or soda ash, can be swapped with sodium bicarbonate for milder neutralizations. Just be sure to adjust the concentration as sodium bicarbonate is weaker. A sodium hydrogen carbonate, known as baking soda, can be replaced by potassium bicarbonate for neutralization reactions or antacid preparations, but make sure the concentration is comparable. Results. Ammonium acetate can be replaced by sodium acetate in buffer solutions, but the concentration should be similar to ensure effective buffering. Ammonium chloride could be swapped with sodium chloride for similar uses in preparing ammonia-based solutions and buffer systems, though the exact concentration may need to be adjusted. A sodium sulfate used as a drying agent can be replaced with magnesium sulfate or calcium sulfate, though ensure that the drying capacity is similar by adjusting the quantity based on their purity and concentration. Sodium thiosulfate, not SO3, often used as a reducing agent, could be substituted by potassium thiosulfate in titrations, photography, or dechlorination as long as the concentration is matched for similar reactivity. A zinc chloride can be replaced with magnesium chloride in catalysis and other organic reactions. However, the concentrations should be aligned to maintain the same catalytic effect. 4. Organic solvents. N-Hexane, a non-polar solvent, can be substituted by cyclohexane or petroleum ether, but be cautious of their varying boiling points and purity, adjusting the concentration as necessary. Toluene can be replaced with xylene in organic synthesis and paint thinner applications. These solvents are quite similar, but ensure concentrations align for identical solubility properties. Eacetonitrile can be swapped with dimethylformamide or methanol, especially in high-performance liquid chromatography. Make sure their polarities and concentrations are suitable for the required synthesis. A diethyl ether can be replaced by acetone or hexane for extractions, but adjust concentrations to keep similar reactivity. Chloroform can be substituted with dichloromethane, which is less toxic and works similarly in separating organic and aqueous layers. Keep the concentrations the same to ensure effective separation. A denatured alcohol can be replaced with isopropyl alcohol for cleaning and solvent purposes, but maintain similar purity levels to ensure consistency in reactions. 5. Reagents and indicators. A Benedict's reagent can be substituted with Felling's reagent or Tollen's reagent when testing for reducing sugars. Just ensure that the concentrations are aligned for accurate detection. A methyl red can be replaced by bromothymol blue or phenolphthalein, depending on the pH range you're working with. Concentration needs to be adjusted based on the desired pH detection range. Ethylene diamine tetracetic acid, a chelating agent, could be swapped with citric acid or nitrilotriacetic acid for metal ion binding, but the molar concentrations should be adjusted for similar efficacy. 6. Miscellaneous chemicals. A magnesium sulfate, a drying agent, can be replaced by calcium sulfate or sodium sulfate. The drying capacity should be checked based on the required moisture removal and concentration. A glycerol can be replaced with propylene glycol for use as a solvent or preservative, but ensure the concentrations match to maintain similar properties in biological material preservation. A distilled water can easily be swapped with deionized water or purified water. These should be free from impurities, but confirm the purity level to ensure no contamination in sensitive chemical processes. Activated charcoal can be substituted with silica gel or alumina for adsorbing impurities. Concentration adjustments may be needed based on the volume of impurities you're trying to remove. Triethanolamine can be replaced by sodium hydroxide or potassium hydroxide for pH buffering and emulsification, but be sure that the concentration is adjusted to achieve the same buffering and emulsifying effects. In conclusion, when replacing one chemical with another in the laboratory, it's critical to match both the concentration and purity to maintain consistent experimental results. Always check the specific requirements of your reactions or processes to ensure the substitutes will perform as expected. Thank you for joining me in this overview of common laboratory chemicals. I hope this has been insightful and helpful for your future research endeavors. Hey everyone, thanks for watching. If you enjoyed this content and want to see more, make sure to hit that subscribe button and turn on the notification bell so you never miss an update. Your support helps us create even better videos, and we really appreciate it. Don't forget to like, share, and comment below. It means a lot to us. Thanks again.